Hello everyone and welcome to Copernicus WEkEO service workshop WEkEO for ice monitoring. My name is Daria, I'm from Novelties, and today we are gonna look at QGIS exercise dedicated to collapse of a Blatten glacier and consequences on snow and vegetation covers. In this workshop we will see how to use data available on WEkEO service and how to use it specifically in QGIS software. And this tutorial is also available in PDF file, in PDF version. If you prefer to see step-by-step procedure written and not to follow it in the video, you can also go to the website and have this PDF file which is provided to you. So for this tutorial, we will first look briefly at the context of our study case. Then we will look at the data which we obtain from WEkEO service, and then of course we will go to QGIS project and do a step-by-step study. So for this tutorial, we will focus on Blatten Glacier, which is situated in Swiss Alps. And its collapse what happened on 30th of May 2025, so it's a very recent event. And the collapse of this glacier triggered a massive debris avalanche that destroyed parts of a nearby village and reshaped the valley within several hours. So here on the photo you can see the aftermath of this collapse. You can see that here the glacier was on a upper part of this mountain cirque, and you can see all the debris, all the rocks and mud that was dragged down, and you can see that it did it was disposed on a valley. And more precisely, we can see it also after in our study. We can see that there are some buildings or villages, there are people and their settlements. So this catastrophic event actually followed a period of unusually high spring temperatures, which caused in its turn a rapid snowmelt and also permafrost thawing in the region, which all together are actually factors increasingly linked to climate change. So yeah, we know the temperature rises, and of course the snow melts, the glacier melts, and eventually collapse. And as alpine glaciers, as they shrink and they melt and they lose structural stability, their surrounding rock faces, all this rock that you see on the image, before they've been held together by this ice, and then this ice actually cracking and melting, whereas nothing more that holds those rocks all together. So of course all these rocks, they become more prone to collapse, and this is very hazardous, high hazardous situation in the mountains. And such events like collapse of Blatten Glacier and many other glaciers, they're becoming more and more frequent, and they are quite unpredictable, and they are very destructive. And that highlights the urgent need for effective monitoring and early warning tools in order to predict. And yes, we cannot actually solve this problem, we cannot stop it from collapsing, but at least we can prevent people, evacuate people, and make some other protective measures. So the data we are going to use for this tutorial is Sentinel-2 images available here on the WEkEO website. You can go yourself to the page and to read more about Sentinel-2, read more about this data. But the most important thing for us to know right now that Sentinel-2 provides, that's a satellite imagery, so it provides images which are tiles of specific places, of all full coverage of the globe, and these are raster images. And as we are interested in a specific event, we would like to have those images, those tiles, specifically close to the date of a collapse, and we know that it happened on May 30th. We know that small movement in glacier was already detected days before it, and which usually quite often, it happens quite often in the high mountains, but it doesn't mean that the whole glacier will collapse, which unfortunately was the case for this time. And what we want to do is we want to have several tiles, several satellite images to see the progression before, like from glacier being a normal glacier to starting to show some changes in it, then to a full collapse. So for that we downloaded 4 different tiles from May 10th, May 15th, May 18th, and May 30th, 2025. And important note, there are more images that are available in this period, like before and after. It's just these images were the most representable because they had low cloud coverage, because there are some images that are closer to May 30th. I think, for example, there's something on 25, 26 of May, and this image was not selected because it was fully covered by cloud, so we cannot see actually anything. So now, as we know the context and the data we're going to use, let's go directly to QGIS. So here, when you open QGIS the first time, that's what's gonna look like, a new empty project. And the first thing that we're gonna do is we're gonna add our background layer, which is basically our map to, well, better navigate and to see things. So for that, we go to Layer tab here, we go to Add Layer, and we choose Add XYZ layer. And then here, if you are new to QGIS and you have it's the first time you open it, you will actually have nothing, and you would need to create a new one by clicking on button New. And here you would set the name and the URL and click on OK. For us, we already have it. It's called Google Satellite Hybrid, and it's basically exactly the same layer you would see usually when you go to Google Maps. And for example, you can see the URL here. Of course, you don't need to pause the video and try to replicate it. This link and some other links to some other type of background layers, they are provided in a PDF version of this tutorial. So as we have it already, we can click OK, we can click on Add and Close. So here it is. Looks exactly like I told you. That's just Google Maps. We're gonna zoom a bit to, well, Switzerland, like this. So in this tutorial, we will learn how to work with satellite images represented as raster tiles. And the images we will use, as I already mentioned, they are coming from Sentinel-2 product. And most importantly, we're gonna look on specific bands of these images, because each satellite image actually consists of several bands, and we will need only specific bands, the bands we will use to actually calculate our indexes. So we will gonna use two indexes, which first one is NDV, or Normalized Difference Vegetation Index, and the second one is NDCE, which is Normalized Difference Snow Index. So basically, these are two indexes that allow us to detect snow cover and vegetation cover, and they work as both of them. They are a combination of different bands which allow us to highlight specific features of a cover and to deem the others that are not important in that specific index. So talking very quickly about this NDV, which is Vegetation Index, well, it is widely used in remote sensing, and it measures the presence and condition of green vegetation. And specifically, it uses two bands, near infrared and red, and it is taking advantage of the fact that healthy plants strongly reflect near infrared light and absorb red light for photosynthesis. So that's why these two bands are used. And the second one, Normalized Difference Snow Index, is used to detect snow and ice on the ground, because snow reflects visible green light but absorb shortwave infrared, making it distinguishable from other bright surfaces like clouds or rock. So from that we know that NDSE index will take into account green band, and SWER, which is shortwave infrared. Since the little scientific part was covered, let's now focus on the technical part itself. So first we would need to import the images from a choose a scene to a QGIS project. And we selected a zone covering the glacier. This area is fully covered by only one tile, which is called T32 TMS. And we will have a look at the evolution of the glacier collapse. So we will load 4 different dates, as I told you before. Well, 3 before collapse and 1 just right after. And for the first exploration of our product, we will import only the TCI images, which is true color images. So basically, it's exactly how we see the image, how our eyes perceive it. So like in true colors, like here, like the map. So for that, we can do it in two ways. First way is to basically use the same approach as we just did with our background layer. And this would be to go to Layer tab, go to Add Layer, and choose Add Raster Layer, because now we know it's raster layer. Here we can browse to our data. Here, this exercise with all of its data, all the information will be provided to you as well as this video. So if you don't want to go to the website and download it yourself, you can already have the data prepared for you. So here we have 4 different products. We'll say it's actually the same product. It's Sentinel-2 images, but it's 4 different images, as I told you, from 10 of May to 30 of May. So that's why we have 4 different ones. So first, let's look which one is the first one. Was the 10. We go to it. We go to Granule. We go to this one. We go to image data, and here you can see actually all the bands I told you about. There's very many bands, but for now we're only interested in true color image, which is the last one, TCA. And we click on open. It's added here. We can add it, and it's added here. And we can repeat the same procedure to add the other 3 tiles. Or what you also can do is if you close this and we go to data again, and for example, let's choose 15, right? Go to the same subfolder and take our true color image and just drag and drop it in the layers tab. And you will see it's also being added to our project. So I just added all the 4 images not to take your time. And now we can start looking at the evolution of the glacier. So let's zoom to the glacier itself, and it is in this region, Switzerland, this one little part. If I zoom in, you will see what I mean. And here it is the collapse of Blatten Glacier. You can see already the aftermath because that's the 30th of May. So let's untick boxes until we have the first one. So our first one, which is 10 of May, this image actually has very high brightness, but we can still see that there's only snow. That's why it reflects so much. Some also clouds here, for example, but we see that it's just snow. It's a perfectly healthy, let's say, glacier. And on the 15th and also on 18th of May, we already can spot the first rock falls, which is very, very apparent. And we can see this clearly darkened area in the middle of our zone, and we see that the surrounding snow cover didn't reduce up to the same altitude, which is consistent with the observations since locals started to witness rockfalls from mid-May. And yeah, it means that it is a rockfall, so rocks fall from here down, and it's not just snow getting it's not melting because the temperature is rising, because all around we can see that the snow cover is pretty consistent here. And the final, of course, is the 30th of May. As I told you, we can clearly see the aftermath of a whole collapse, like its area became much wider and bigger, and it reached the valley. And you can see also, if I untick this box, you can see that here was a village, right? And some houses and some buildings here. And on 30th of May, we can, well, we do not see those buildings anymore. It's fully covered with rocks and mud, and also like here there's been also some flooded area. So looking at the true color images of Sentinel-2, we managed to spot before and after of a glacier collapse. So now, as we saw it visually, we want to have more quantitative analysis of it, and for that we will move on to our indexes, as I told you, our vegetation and snow indexes. For that we would need to add the bands for our 2 indexes. So we would need band green band, red band, and near infrared and shortwave infrared one. And since there are a lot of bands right now to add, and we're gonna make a lot of calculations with it, we will a bit reduce our study to only 2 dates, so 1 date before the collapse and 1 just after. So we'll focus only on 10th of May and 30th of May. And as I already showed you how to add the tiles, we're gonna do exactly the same procedure. So I open my folder with the data, and we are right now for 30th of May, which is perfect. And what I need 4 different bands. So I need B4 and B8. So I'll hold Ctrl and click on B8. These are two bands that I will need for vegetation index, and I will also need B3 and B11 for snow index. So I did like that, and I drag and drop them. I will add the same bands for another date, and I'll come back to you. Now all those bands are added to our project, but it is quite messy altogether. So let's organize about our space by creating groups. So right click here in any empty place in a layer tab and click on add group. In there we would name it, for example, we would name it NDVE, and we will drag it up and we will place bands that we would need for this index directly into this group. So it would be B4s and B8s. We choose them by clicking Ctrl and now if you want to untick all this layer, just untick for one group, and you also can close it like this, so it's more so you see less layers. So we'll do the same for the other groups, also arrange them inside, and I'll come back to you. So now we have three groups, one for vegetation index, one for snow index, and the third one is for true color. And for now, for true color, we do not care anymore. We can close it and untick it. And we have those 8 tiles we're going to work with. So 4 tiles per index, 2 tiles per date. So like this, we'll have 2 indexes for 2 dates. But those tiles are quite big. If we unzoom again, we will see that we have a big image that covers lots of other different regions, but we are not interested in. We are only interested in this specific part. And raster images, well, they consist of pixels, so they have a very high quality, very high resolution. That means that they're also very heavy, very bulky, and all the process that we want to do next in QGIS will take much more time if we're gonna keep those images intact. So what we're gonna do, we're gonna clip them only to the region we are interested in. So for that, we will use the tool in a raster tab here, extraction, and we have clip raster by extent. Perfect. Here you can set different parameters, and input layer you see is a raster layer, and clip and extend just extent you set yourself, and you can run it, and then you can come back and run it again for another tile, and then again, which is quite long process because you would need to do it 8 times. It's a bit too much. So I will show you how to do it faster, and for that we need to run it as batch process, and for that you need to click on this little button here. So here basically it allows us to set the parameters for each input layer and then run it all together at the same time. So first let's click on autofill here in an input layer. We put here and we will choose select from open layers. And here we will choose the layers that we're interested in. So we are only interested in in the bands. So we're not gonna take true color ones, just the B3, B4, B8, B11. Okay. And like this, you see they are all added to our list. Next, we will choose a clipping extent. And the clipping extent, we will click on these 3 buttons and we will use draw on canvas. So that will throw us back to our map on which we're gonna draw the extent we are actually interested in. And for that I will activate our true color image because it is clearer like this, and I zoom in. Okay, so this zone is more than interesting for us. I will try to cut it. No, sorry, I don't know, maybe something up, no, too low, something like that, very small area, but really only includes the area of glacier and its collapse. That will be enough for us. And then you set it up. You can click on autofill again and click on fill down, and it will apply exactly the same extent to all the other layers we added here as input. And last but not least, we need to set the clipped extent one, which extent is already on a parenthesis, which means which specifies the output of our procedure. So basically the output layer that is gonna save. We click on the 3 points and in our dedicated space, dedicated folder, we will choose how to save it. So I navigated to my folder, and we will set the name as cropped and underscore. I save it, and when I click on save, there's a new pop-up window that appears that asks you the settings of autofill. So basically it asks for mode and parameter to use, and if your mode is do not autofill, of course there's no parameter to use, but we want to use the parameter values, and parameter to use would be our input layer, which basically means that it will automatically set up the name with cropped as a beginning, and then it will, after underscore, it will continue with the name of input layer because we chose it. Click on OK, and you can see, you can see that the new layers that are going to be produced is they are cropped, then underscore, and the name of each input layer. We need to tick this box, load layers on completion, which basically allowed us not only save those two files but also add them to our project. And then we click on run, and we wait a bit, and you see here that one by one they are processed, and also here they are added. When it's finished, you can close it, and well, now we have a lot of layers, which I'm gonna rearrange a bit. So now, as I rearrange them, I put the crop layers back to their supposed group, so to the snow index and vegetation index, and once again, I don't need the true color anymore. And you can have a look on those bands, what do they represent. And here you can see that they are indeed cropped, and you can see that the bands are actually, well, they're only in a grayscale, and not really, like, for our eyes, we don't really understand what exactly is happening there, but that's what satellite sees in different bands, and that's what we will use for our next step. And this step is to calculate the indexes themselves. So for that, we'll use a raster calculator function. To find it, you go to processing toolbox search bar, and you just put raster calculator, and it's going to be here under raster analysis tab. If you don't have processing toolbox by any chance, for example, sometimes it looks like that, so you just find a toolbox, a little gear icon here, you click on it, and it's here. So we go to raster calculator, we double click on raster calculator, and here it is, our window. So for raster calculator, the main most important part is the expression. So basically the expression allows us to combine in different ways our raster layers, our raster tiles, for example, and it is the one that we're gonna use the most. So now let's first calculate snow index, for example, and for snow index we would need our, well, first let's go to our cropped layers, and we would need band number 3 and band number 11, as you can see here, and it would be band number 3 minus band 11 and divided by the sum of them. So band number 3 for 10 of May, yes, and we deduce band number 11 for 10 also, like this. Do not forget the parentheses because we will need to divide it after, like this. I'll do that. And here we would need to divide it by the sum of them, so this plus this. Let me double check. 10 of May, 10 of May, 10 of May, 10 of May, B3 minus B11, B3 plus B11. Perfect, and expression is valid, so it means that it's exactly what we, but arithmetically it is good. And the next thing, we need to choose a reference layer, and the reference layer can be any cropped one what we used. So for example, we used B3, right? So let's choose this one. We will choose a project CRS, and we would need to save it to keep it for the future work. And we navigate to our folder of results, and we call it NDCI, and it was it was 10 of May 2025, and it's in a TIFF format. So we Click OK, we run, and it produced us a result like that. Let me put it up. That's our result. And now we're gonna repeat the same procedure by just changing the parameters. So basically we can change parameters here, go to parameters, and we change them and rerun. Or, as I already explained you before, you can try to play with run as batch process option and to see how to do the procedure by running it as a batch process as we did before for cropping. So I'm gonna do the same steps for the other snow index for 30 of May by changing only the date, and also I will do the same by changing expression to vegetation index, in which we use not those bands but bands 8 and 4, and it's band 8 here minus band 4 and then band 8 plus band 4. But again, if you feel like completely lost and it's not very convenient actually to like just copy paste from a video, don't forget that all these formulas are provided in a PDF file as well. And after all those layers are produced, we can close this window and we will see them. So for example, this one is our vegetation index for 30 of May. You can see our consequences of a collapse here. And on 10th it looks like this. And for the snow index, we see this on 30th of May and this for 10th of May. But this representation, this color scale, like grayscale, is not really what helps us to understand what actually happening on a picture. We're gonna adjust for styles of these layers to understand better what is happening. So for that, let's start with our snow index. Let's double click on it, open its properties and go to symbology here. And we will change a render type from single band gray, as you saw on a picture, to single band pseudo color. And we're gonna set the minimum to here minus 0.4 and the max to 0.8. A label precision, yeah, 1 is enough. We change mode to equal interval, set 5 classes, and the most important is a color ramp, which will allow us to see it better. So as it's snow index, let's apply blues color ramp, and we will make sure that it is from dark to light. So we click here and we invert it for color ramp, so it is from dark blue to white. We click on apply. We click on OK, that's how it looks like now, and we will copy paste this style by right clicking on it, going to styles, copy style, and we're gonna choose the second one for 30th of May. We're gonna right click, styles, paste style. Like this, they both have the same style. So basically, by adjusting this color map for this layer, for snow index, we wanted to highlight that in white these are snow cover, and in blue there is no snow, and of course between them is a transition. And well, here you can see that also water is considered as could be considered as something in the middle, but that's not the most interesting part for us. Here, for example, we see that on the area, let me overlay it with our true color. For example, this one, right? So yeah, where we see the snow, the snow index has a white parts here, and there's no snow, just in the valley it's dark blue. And for the after collapse, we see that like clearly the big dark blue part, meaning that there's no snow, and it's not only in the valley but it's also on the glacier, on the altitude among the other snow. So we will do the same exact procedure to adjust the style, but now for our vegetation index. So we double click on our index, vegetation index, and we do basically the same, but now we'll set minus 0.2 to 0.6. Also 1, also equal interval, classes will be 5. And for now, a color ramp as its vegetation and the lack of vegetation. Let's choose how is it called actually? Ah yes, okay. There's a color map that we will color ramp, which we will use among all color ramps because it's not here in the usual ones, and it's called this one, brown green, I suppose it means, and we want it to be in from brown to green. Yeah, so exactly like that. So we apply, we click on K, we also copy the style and paste it, and here we go, we have our image. So basically this index, this picture, shows us where is vegetation and where is no vegetation. So in green there is vegetation, and brown there is no vegetation, and well, a transition between them. And you can clearly see that in the valley we have vegetation, we have some green things, and you see that more we go out of the valley to the slopes and into the altitude, we see that there's no green, there's only brown, meaning that it's either, well, mud, rocks, or snow, because, well, we don't have the same radiance as vegetation, so it's not spotted as vegetation. Also water, you can see, is also in this color. And if we look at 30th of May, here we go, we can see clearly that the part of vegetation what was before in the valley was covered by rockfall and mud brought from the glacier after its collapse. So now we saw how the terrain and its condition changed with the collapse, but we still want to better highlight this change, and for that we will create a difference map between the two dates. So difference map means the date after the collapse minus the date before the collapse, and these type of maps are very valuable because they show us visually, how to isolate the areas of greatest change, making it easier to spot the damage. So rather than comparing these two times like this, we can actually see the difference in the terrain, like in which we gained, like for example for vegetation, the difference between will show us in which we gained in vegetation, which we lost in vegetation. So for that we will use again raster calculator function, which is here, and now we will use different expressions, and for now I will copy paste the expressions that we actually have in our PDF file. Like this, you can see that actually you can just copy paste it and it will also work. So we will first do it for vegetation index, and it's basically, as I told you, it's from May 30 to May 10th. And we will choose one of them as a reference layer and project and save to file, and we will save it as NDVE difference, like this. Save it, run it, perfect, it's done. And now we'll do the same for the snow index, like this, and here we change it like this. So now we have two new layers. Let's drag them above, and also let's adjust the styles as we did before. And for now we will not choose the same color ramps we used before. We're gonna use different ones that will allow us to highlight better the change. And for that we will use another one from all color ramps, and it's called red blue, this one. We will invert it from red to blue, yes, and let's put minus 0.5 and no wait, it was -1. Alright, okay, so no, we keep it -1 and put 1 because it's snow index, yes, okay. And I think I can apply, okay. And for another one, for vegetation, we will change it to minus, okay, here's minus 0.6. Now maybe to 5, actually, yes, to 5. And here just to 5. We apply, and okay. So now we basically have two new maps, and if we look at the vegetation one, we'll see that there's mostly the zone is blue, dark blue, or some like I don't know, beigey color, but here we have a red. And here, exactly in red, we have a loss of vegetation, and we know that exactly as these parts were covered with mud and rocks, it means that there's no vegetation anymore, whereas so that's why it's red. And blue is basically a gain in vegetation, which is kind of, we have not much, but we have some here, and it makes sense because, well, also between 10 and 30 of May, there's a lot of days passed, and it's also very hot. It's been a hot time, so of course the snow melts, giving the way for vegetation to come back. And in the kind of whitish grayish zones means that there is basically no change whatsoever, so vegetation stayed in the same condition. And the same we can see for snow index. So basically for snow index, well, here in blue is a gain, kinda. In the valley, there's no change in the valley because there's no snow in a priori. And in red, it's a loss of snow, and you can see that on the slopes there's a lot of red parts because, well, it makes sense. First of all, you can see here there's a lot of red, even though it's not corresponding to our collapse because, as I told you, again, the temperature changes and snow melts. But also, it's either to that or either to the parts of the snow that actually collapsed and was covered with rock fall, and all the mud would be triggered here. What is important to see here is that this one is snow index, right? So here we can see clearly, also know how our sequences of our collapse looks like, and we see that here this is the part of a collapse of snow, right, which was covered before it was covered snow, now it's covered with rocks, but we don't see it here specifically because, well, there were no snow, so of course they didn't detect it. And the opposite for vegetation, we see here the change, but we don't see, well, a bit here, but we don't see it much here on the snow because it was not the index for detecting snow. So what is interesting for us to see is how to like overlap the patterns of these both of these maps in order to exactly delineate the main collapse zone. So for that we will use a bit some other tools, but first we will want to convert our data to vector layer, because for now we still work with raster layers. But before we do that, we will first make so-called mask, like we're gonna create a mask that will help us actually to delimit this collapse area, and then we'll first create this mask and then organize it. So again, we go back to our raster calculator, and in the raster calculator we choose this expression, which basically says highlight in white the zones that are less than minus 0.05 for vegetation index, and that or they are less than minus 0.5 for snow index. And this expression has been chosen by me by trial and error method. I basically ran several raster calculations to see which threshold actually works the best to like select the zones that are affected the most by collapse for both vegetation index and snow index, and those two numbers actually allow us to have a quite nice representation. So for example, a threshold for vegetation index, it captures even moderate vegetation loss, which can result from debris covering grassy or forested slopes, like we saw in like here, you see. And the threshold for snow index, which is this one, it isolates areas with substantial snow disappearance, which can be due to melt or being buried under collapsed material. And using both conditions together allows detection of both ice-covered and vegetated areas that were both affected by the event. So like this, we have a more complete outline of a zone. So let me continue with setting of parameters, which we would need to difference. So we would need to set difference. Okay, and then CRS op, and let's save it to file, and we will call it raster filtered, maybe masks filtered. Okay, so save it, run it, and close, and here we have our new layer. which basically means that in black we have all the zones we're not really interested in, and white are the zones that are falling under this condition. So the white are the zones that falling under threshold, both for snow index and vegetation index. And we can see clearly that here it is quite nicely outlined, even though we have some zones of basically it's mostly like snow or whatever, like some zones also of snow loss here on the slopes due to snow melting. And yeah, I mean, it's quite normal that radians of these pixels were also falling under this threshold, but the main point is that we have our outline and it's pretty close to what we actually would expect. So now let's polygonize it. For that we go to raster and we go to conversion, polygonize, raster to vector. So here it's clear, raster filtered as our input layer, and then name of field to create is, well, let's say drop, by meaning drop in vegetation or snow cover. And we will save it as what was it? Raster. Oopsie. Oh, it was raster filtered, and let's say it's raster, but it's vector, so raster vector. And important note, you see that now it's in a shape file because it's a vector file now. So first time we actually have a new type of data we use and see in QGIS, and it's not raster. So let's close it, and it looks like that. So basically it's a new layer, which is a vector layer, which repeats all the features of a raster layer by creating many small polygons of each feature. And you can open the attribute table of it to see that there's actually many polygons inside it. But we only interested in the drop, right? In the change of a cover, and we saw it in what it's zone in white. So as I just opened the attribute table for you, you saw that for each polygon it had a drop value, and it was all 1, basically, and except for everything else, but like the background was black. So for that we will filter our vector layer. We right click on it, we go to filter, and in the pop-up window we put drop equal to 1, click on OK, and now, well, I will I will leave this one. Now we can see that all the zones that had a drop equal to 1, to basically change what was recorded, they are now only selected and the background is not selected. But again, as I said, there are so many other polygons that we are not interested in, because we know that it's not a change due to a collapse, but due to other reasons. And for that, we will select only our area, and we would need to find this little icon here, which is called select features by area or single click. So we click on it, and we will click on our zone, and you see that it's actually turned yellow. And basically it means that all this feature is one feature, it's one polygon. It was detected as one unity, not connected to those small ones. And what you can do also, if you want a really precise study, you can also take all those small polygons that are actually, well, we see that they are also in the area of our collapse, but we're gonna simplify the task and we're gonna only keep this one feature, and we want to save this feature as a separate vector layer to facilitate the future work of it. For that we show the feature, and we right click again to on our raster vector layer, and we go to export and save selected features as. So it proposes format as default as shapefile, which we need. And then we browse, we choose, and let's call it collapse area, because that's what it is, right? We save it, we click OK, and see what, let me change it, okay. And we see that there's been a new you see that there's a new layer been created and added to our project, and if you activate it, you see that it's only the feature we chose. But again, if you also chose small areas, small polygons, somewhere in the middle, we would be also saved to this new layer. So the last but not least task of this tutorial is to actually calculate the area difference, because that's what we want to know, right? We want to see how big is actually the how big is actually the collapsed area, how much it covered, and to like estimate the damage done. And in QGIS we actually have two different tools to calculate the area. And first one I'll show you both, and let's look at the first one by right-clicking on our collapse area layer, go to Open Attribute Table, and here you can see that as it's only one feature, it has only one column, one line in it. And we will activate editing mode here. And after it's activated, we can see that there's, you see if I deactivate, there's some buttons available now, but we will use Field Calculator 1. We open in a new window. We take a box, create a new field, yes. The name, we would call it area. We want it to be decimal number, so it's more precise, and precision, let's make it 4 to have better presentation. And we would need to set an expression again, and you can also look around in this tool and see different expressions that it can propose already by default, but I will copy paste one what we decided. It is area but multiply by 10 in -6, because this exactly because that's an area in kilometers, not in meters. And it's already gives us a preview for our first feature, which is 3.05, and we click on OK. And after we click OK, we can see that there is a new column added to our attribute table with a new value. We need to untoggle the editing mode. A little window will appear asking if you want to save the changes to this layer, and you click on save, and like that we learn how to calculate the area difference for this layer, and how to store this information in this layer. So even if you close the QGIS and then you reopen and open this layer again, or you open this layer in some different application, you will see that there's a new column with a new information stored in it. So it will be like, so you have a trace of it. And here what's important is, as I said, we can say roughly 3 square kilometers. And 3 square kilometers sounds like 3 square kilometers, what is it exactly? Like, it doesn't have a very big, maybe it's not very clear how much is it, but I will give you a little scale, is that it is roughly the size of 400 football fields. So football field, imagine football field, then have a 400 of them, and that's exactly the area of collapse of a Blatten glacier, which shows massive scale event with enough debris and destruction to bury an entire village, as we saw. And you also, like, you saw, right, that from like on 10th of May nothing happened, on 15th some rocks, whatever, 18th still rocks, and puff on 30th of May, just like 10 days after, there's a huge collapse. There's a huge area of 400 football fields which is fully covered with rocks and debris, and the whole village is destroyed, is covered by rocks, and yeah, just 10 days, 2 weeks, and this event happened and brought this scale of destruction, which is sad, of course. But moving to more practical parts, the other method of calculating area is a bit faster and a bit easier way to calculate it, but it does not allow you to store the information for later use in the layer. And this would be this little icon here with information, and it's called, what's it called? Identify features. So you click on it, and it has a little cursor that changed. So you click on this area, and it asks us like which one you like, because apparently we can see that there are several layers that are overlapped one over another, but we are interested in the collapse area. And when you also like choose it, you see that it's highlighted. Click on it, and there's a new window here, identify results, that's showed here. And it shows in actions, it shows the columns that are already present in this layer, which is drop, which we created before, and area, which we created right now, and also derived. And if you open the drop down menu of derived, you will see that area here, ellipsoidal area, which we need is 3 million, right? Yeah, 3,056,000 and something square meters, which if we translate to square kilometers would be roughly 3 square kilometers, or exactly the same what we already calculated before. So basically, it gives us exactly the same area with two different tools. The only difference is between the two is that the second one is much faster. You just click and it gives you information. So if you just need some scale and you're okay with that, just need to know that works perfectly. But if you need to store this information somewhere, specifically in this vector to use it further, of course, the first one is more preferable because it will allow to exactly store this information down there. And on that note, that was the last exercise of this tutorial. And in this tutorial, we saw many things actually. We studied this specific event by using data available on a WEkEO service, which are satellite imagery represented as raster tiles, raster images, also separated in bands. And we saw how to import those tiles in different ways. We learned how to work with them by cropping them in batch process. We learned how to use raster calculator a lot by calculating vegetation and snow index. We learned how to compare those images we have to see exactly the evolution of a collapse of a Blading glacier. And we calculated the differences. We calculated the main difference to highlight exactly to outline the zone of a collapse. We learned how to convert this raster layer to vector layer to be able to quantify it better. And yes, we learned how to filter. We learned how to calculate the difference into calculate the area of a difference into distinct ways to be able to put a number on this event, because we saw what something happened. We saw what not great, right? That we saw what the change on the terrain, but we didn't know what it represents in terms of number, and now we put a number on it. So that was it. And a little reminder for you is that you are free to recreate this tutorial, but also to apply some creativity and maybe expand it or shorten it however you want. That's the good thing about QGIS and also about the data available on WEkEO platform, that you can combine with other different data. For example, how you can expand this tutorial is by finding some atmospheric data, some weather data on WEkEO to, for example, see the temperatures and how temperature changes before the collapse, and just like to see the temperature change in 3 months prior to the collapse, to see how exactly it might affect the snow, rapid snow melt, and so on. So you see, you can have additional data. You can maybe, even without the data you already have in a project, you can create some more layers. You can use some more tools of QGIS to have a more in-depth analysis, whatever you want. And also this data and all our data that you can find on WEkEO, you can use it for different study, completely different zone. Like it's not, it's just an example, So it's up to you to actually create something interesting and to learn something new out of these tools. So that was it again. I hope you enjoyed this tutorial. I hope you learned something new for yourself, and I wish you all the best. Bye bye.